It's on a black screen right
Professor,
now.
we are not
Yeah,
able
yeah,
to
yeah,
see.
yeah, 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 yeah. I got it. 1 sec. Sorry.
Thank-
That's good.
There,
All right.
no.
There you go. All right.
Yeah.
Okay. Sorry about that. Okay, so we have our coil, and then after the coil, we usually have that overload, right? Normally closed overload. So if the motor overheats, that's the start of our latching circuit, and then we have this parallel contact, right? And it's important that if we call this M1, then this is M1, right? Then we're calling this whole thing up here M1, right? So this would be contactor M1. And we have line 1, line 2, line 3, T1, T2, T3, right? Those are the main contacts, the normally open contacts. When you close those, motor comes on. The motor also has auxiliary contacts, so sometimes they're at the side here, right? You might have it normally open, normally closed, right? Like on those larger black ones that you're working on, the ABB ones. So those are auxiliary contacts. And the auxiliary contact was here, and that was auxiliary contacts are used for control, right? Auxiliary contacts are primarily used for control. Okay. So again, just to go back through everything. So right now, if we're looking at our latching circuit here, line 1, line 2, and mostly our latching circuit was 120, right? So line 2 is a neutral, 120 volts. And right now, my neutral side's all connected, normally closed, everything's connected up to here, right? So you might be asked like something like if you saw a picture of something, I might ask you like right now, if I were to measure from, let's say, A, B, and C, what would the voltage be between A to B, and what would the voltage be between A to C? A to B first. What would that be?
0.
Yeah, so if we follow it, this is closed, right? I'm highlighting it green because green's representing like that's the line side, right? And that's everything that's connected right now. So that's our live power. It's not actually making it to the coil, so the coil's not on. But right now, A to B is the same potential, right? So if I put my meter at those 2 points and I measured voltage, I'd measure 0 volts. If there was no power and I was measuring for continuity, if I measured from A and B, I'd have continuity, right? It's all the same. It's all connected. A to C, I would probably expect to see,
120.
right? So kind of maybe identifying voltages would probably be good, right? Understanding like where there's differences. I would probably expect you to, know how to draw something like this at the minimum. You're going to have a schematic somewhere on your test. You're going to have to draw a schematic. And you're probably looking at one of the most important fundamental schematics right now, the latching circuit, right? And of course, if you're to draw that, like, you'd want to show all the parts of it. And there's only really 5 things, right? There's a start and stop button. There's the coil, the holding contact, the auxiliary contact that we're using in parallel, and then the overload, right? That's a pretty fundamental basic latching circuit. You could probably expect to see something like that, right? I would also probably expect you to be able to maybe complete a diagram, right? So when we had the manual starter, for example, what was the manual starter? The manual starter was one of the first ones we did. It just had 2 push buttons, right? It had the red and black push button. What was the schematic diagram? What was all part of that manual starter? There was only really 2 things. There was a set of contacts, right? Normally open, that were controlled by the push button. And then what was the other thing? What was the other thing The other thing was, what's the part on the bottom here that I want to draw? Starts with an O.
The other no?
Yeah, the gold bits, right? So the overloads. Okay. So the overloads. That was it. That was all there was to a manual starter, right? And then they went to the showed like the connection to the motor, right? The main parts of the manual starter though were the overloads. Right. Okay. So that was that was pretty important. Um, I would also expect you maybe like if I gave you like a diagram or if I drew connections and I gave you the information, like the forward and reversing contactor, we had 1, 3, 5, 2, 4, 6. If you had a diagram, sort of like you saw like on the back of that cover, I would probably expect you to be able to complete wiring or connections to that device, right? I wouldn't expect you maybe to memorize that, but I would expect you to be able to um, work off information just like you did in the lab. Okay. How do you test fuses, contacts, normally open, normally closed buttons? What setting in overloads? What setting do you usually use on your meter? What's that setting called?
The ohms.
Yeah, you're testing for ohms 100%. So testing for resistance works, and the convenient way to test resistance is to measure using the first setting on your meter. Resistance is on your meter, but before you get to resistance, it goes to
Continuity.
exactly. And I think your meters, anything under 100 ohms, it beeps, right? Which is just quicker to hear it than actually to take time to look at it, wait for it to measure down. Just quick beep. That's under 100 ohms, and then basically you got continuity. So that's the good way, right? And then of course, if you have continuity, is a fuse good or bad? If it's showing continuity, is a fuse good or bad?
Good.
It's
Good.
good. It's good.
Typically, yeah.
Yeah.
Yeah. All right. So that's how we would test. Um, explain how you would test current with your clamp meter. So it's been a while since we did it, but you have the clamp. How many wires should you put under that clamp?
One wire at a time.
One wire at a time. You could put more, but the problem if you put more, it's just going to measure the difference, right? And typically you don't
Okay.
want that. So like if you're measuring like a hot and a neutral, right? If you're measuring a hot and a neutral, then you're just gonna like read zero, right? It'll cancel each other out. So sometimes it could be good to find unbalanced current, but typically just one at a time. Okay. It just does that through the magic of magnetism. All right. So that's that. Identify good troubleshooting practices. So what's the number one thing to check for when something does not work? What's the number one thing to check for?
Like button, press and start button.
So I come over. What was
And
something
then
that sometimes people forgot to do when I came over and unlocked their station? It
The
was all
number them.
number them, but also maybe right the very first thing. What do you do? What do you got to do? We got to unlock everything. What else you got to do before they even get power? You have to
they like check the
Yes.
power first and then fuses.
check power. First
Yeah.
thing, always, right? Sometimes it was because we didn't plug something in. We forgot to plug something in. Sometimes it was because, there could have been a fuse blown or the disconnect was off. So good troubleshooting practice is always, always, always check for power, right? Okay. So that's definitely the first. And then once you check for power, and then you can work your way back from there. And we kind of learned too, like if I had this circuit here, my latching circuit, and it wasn't latching, where would I start looking? A, B, C, D. So I press my start button, my motor runs. As soon as I take my finger off the start button, it stops. What's probably going to be the problem here? Where should I start looking? A,
It should
B,
be C.
C, right? It's going to be right at the latching contact. And that could be as simple as this wire was just not connected, right? Or loose connection, or you put under the wrong terminal. But as soon as one lead is open, this might as well not exist in the circuit, right? Only takes one small thing. It could even just be a screw or something, right? As soon as one wire is not connected, this is completely removed. And that makes sense. Oh, it's just jogging. Well, because that's effectively what I have, right? So you always can like look at the functionality to see what the issue is. Sometimes the motor started right away. And then you press the stop button and the stop button would stop it, but the motor was starting right away. So there was a good chance that somehow, maybe somehow we were bypassing, right? Somehow we mixed the wire up and we were bypassing our start button. So always kind of look for like, what is the reason? Why is something not working properly? Okay. All right. So I mean, I wouldn't ask you anything like too crazy, but like common issues. So obviously one, check for power. What would happen if we had that forward reversing circuit that we did last week, the last circuit we did? So we had that forward reversing contactor. That had wait, what was special about that? What did it have in between? This is probably important, right? I'm not gonna waste any time in this class. What's that part in between there?
Interlock.
Yeah, there's two types, right? There's the mechanical
Yeah.
interlock.
Mechanic interlock.
Yeah. Yeah, that's the one that's physical, right? We all saw that when you tried to press both in at the same time, you could only push in one or the other. That was a mechanical interlock. But then we wired an electrical interlock in there too, right? We used a normally closed contact, say forward, and then maybe there was like a reverse coil, right? So that was the electrical interlock. So if the forward motor was on, you couldn't energize the reverse. So that was another type of interlock. But let's say for some reason we forgot to wire our interlocks, and then we were pressing like the forward and reverse button at the same time. We saw, I kind of demonstrated this. What happened? They would both try to pull in, right? Sometimes they would like chatter, but they wouldn't short because of that mechanical interlock, right? Okay. Which way do you, and speaking of changing directions on a motor, which way do you check direction on a motor? So I have like a little motor connection pants here. What's it going to be? A or B? Where do you check for like rotation? If it's going to go clockwise or counterclockwise?
A.
Yeah, what do we, and that's the standard is opposite of the shaft end, right? That's what we're going to check. Okay. All right. So there was also probably, so let's go else. What else we got in here? So identify information from a nameplate. It's probably important, right? So I identify, let me just do this here. There we go. So identifying some important information. So FLC and FLA is super important, right? If a motor has 1 amp, FLC is 1 amp, and that motor is actually running at, it's turning fine, it doesn't sound bad, it's spinning, but it's only drawing 0.6 amps. What does that tell you? So it should be 1 amp, but we're actually getting this. What would that tell you about the motor? Full load current means the normal current when it's running under
On the low.
load, right? And then what did we find? You remember when we tested this, we measured current, it was all way under. And the reason why is because our motors aren't connected to anything, right? So FLC is important because FLC is that's what the motor should run. So if you have a motor that's 1 amp, it should run at 1 amp when it's working normally. If it has less, it could be under load. And if it has more, if it's actually 1.3 amps, what does that mean? The motor is
Overload.
overload, right? And there's something when and there is a device that we have to protect us from that, right? And that is our overload device. And our overload device is basically set based on our service factor and our FLC. And there's a multiplier, right? So maybe that would probably be a good thing to tab out in your code book, that calculation, how to size an overload, right? Section 26. So again, bring your book, right? You can tab that out. You're probably going to have to calculate that. And by say probably, I mean, like there probably will be a question, right? It may be a multiple guess, but if I have a multiple guess with math, there's probably going to be, you know, every which way that you can calculate it right and wrong. Okay. So FLC, full load current. I mean, you should be able to identify like the different symbols. So normally open, normally closed, push buttons, normally open, normally closed, contacts, right? The coil. What else here? So may or may not have a question asking you how to like complete the terminals, which you've done every single lab. So in these motors, right, there is T1 to T9. There's 9 leads, right? And we can connect them different ways. So you might have to just identify like the difference between low and high voltage, right, connections. So, and whenever you have a motor, if the motor has multiple voltages, so a motor could be 120/208, 208's the high voltage, right? A motor could be 347, 600, right? 600 being the high voltage, right? So whatever the higher number is, that's the high voltage connection, always, right? And if there's only one voltage rating, you're not going to have multiple voltage connections. But you'll always have like those 9 lead motors. That's very common, and usually you'll have to connect them a certain way. Sometimes those 9 leads are connected for dual voltage motors. Sometimes it's to change the speed of the motor. But it'll always give you the diagram. So just like the diagram we had in your very first lab, right? Or the same one that you see on your on the station or on the motor itself. And then again, whatever we had there, we had to physically, you know, do our connections a little differently, right? And that was T1 to T7, T2 to T8, T3 to T9. And then like 4, 5, and 6 just interconnected with each other. What's the main difference between fuses and overloads? Both protect from too much current. What's the main difference between a fuse and an overload? Could you tell me anything? And is there any difference? What would be the main difference? A fuse and an overload.
Like fuse protects the circuit, and they
So both are, you have to fuse everything, right? So like you have to put overcurrent protection for everything. So if you're at a panel, right? You're at a panel and from your panel you install a 3-pole breaker, for example, right? You're gonna size this to overcurrent protection. So it could be fuse, could be a breaker. Or you have a splitter, doesn't matter, whatever it is. And then you get a disconnect, and the disconnect has fuses in it. And then this disconnect goes to a motor, right? So our disconnect's going to have our overcurrent protection, fuses. And then over here at our motor, well, we don't need more fuses at the motor. We already got fuses on that branch circuit, right? So this circuit only does the motor. But we need probably overcurrent protection. We do that with our overloads, right? And so the difference is, well, both fuses, this is the branch circuit, the fuses and the overload are sized based off of the FLC of the motor. Both things are sized from the FLC, so then again, what's the difference, right? The main difference is that the overloads typically are not time delayed, right? Overload is typically not time delayed. Breakers inherently have a time delay, and you can get fuses that have time delay. And usually with a motor, you need to use fuses with a time delay because when you start a motor, it draws like 10 times the current it actually should until it gets up to speed. So that's one of the big differences. And because of that, fuses are usually sized a little larger. Fuses can be sized larger than the overload to allow the motor to start and run. So a fuse will protect the circuit and the conductors, and usually if the fuse trips, it's like what we call, it's an electrical failure, typically, right? If the fuse blows, it could be a short, the motor could be failing. It's something usually significant. If the overloads are constantly tripping, it could be because that you have that 1 amp motor and it's drawing like 1.2 amps constantly. It will trip the overload. And that's usually a mechanical issue, usually, if everything's sized right. So maybe you got a motor and the belt is there's too much tension on the belt and the gearing, or the motor is a pump and there's too much back pressure and the pump is having a hard time, it's working too hard, and you're drawing a little bit more amperage, that will eventually overheat the motor and burn up the windings. That's what the overload protection is for. Okay. If your fuses are sized small enough, they can actually provide overcurrent protection too. But typically, fuses are larger sized, right? If they're sized usually a little bit larger to allow the motor to start up without blowing them, and then they're time delay, whereas the overloads are not. Overloads are to protect the motor itself from overheating and overloading. Okay. And the service factor rating, right? The service factor rating is going to basically tell you, exactly the multiplier that you're going to use for, like, say, something like your overload, right? Service factors, like if you have a service factor of 1.15 or higher, or 1.15 or lower, it's going to be, multiplied by 115% or 125%. All right, section 26. All right. I would probably expect you to be able to draw any schematic diagram. Now, again, probably not the most complicated ones, but probably I would say the most important one, and the most important control circuit. Everything we did built off of it was the latching circuit, right? So I would probably expect you to be able to do a simple schematic of a latching circuit. And maybe not all the fuses and transformer and everything, but starting from what I just drew recently with the push buttons, right? 2 push buttons, auxiliary contact, coil, and the overload, normally closed overload, that should be like a minimum, right? You should be able to identify the parts of those contactors, like main contacts, auxiliary contacts, the difference between, right? Purpose, if you saw like, a auxiliary contact in a circuit, what's the purpose? So in this case, for example, we know this red one, this is an auxiliary contact, but we call that the holding contact, right? That's the purpose. It's an auxiliary contact, latching. Holding, that's its purpose, right? Just like sometimes if we put another one here and it was like normally closed and this was M1 and say this is M2. And then basically this would mean, oh, if we're running M2, if we're running the second motor, then we can't run M1. And that would be, that purpose of that auxiliary contact would be an interlock, right?
Yes, I am.
Okay,
You
what
scared
else?
of rivals. You're not innocent.
No,
Um,
I don't scare anyone. Yo. Okay, wait, I'm gonna stop using my mic. Oh my god. Is this still green?
What else? What happens if a motor single phases? What happens if a motor single phase? So we have a three-phase motor, a three-phase motor, and what single phasing means is we lose a wire. What will happen? Will it turn slower?
Why is it taking shortcuts?
Will it turn at all?
Stop,
sure.
stop, stop.
Do you-
stop,
do you remember?
Stop, stop, stop.
If not, this is probably a good thing to remember. What will happen?
Hey guys.
And it is.
Unbalanced current, maybe.
Get away
Hey,
from
wait, please don't
me.
get me. I'm innocent.
It will lock up.
I'm innocent.
It won't turn. Right? You single phase the motor, it's gonna lock up.
Never mind. Oh,
So this motor here, so if we have a motor,
Now, 'cause he's coming for me.
there you go, get out of here. We have a motor,
Yes, I-
three-phase motor. And then we got three phases, but
Go to Glizzard.
line 1, line 2, line 3, we forgot to connect a wire or one of the wires isn't connected properly. All right, so this is a 2.8-volt motor. It's going to not spin. And so when we turn it on, what's going to happen? Let's say this motor is only supposed to draw 1 amp, right? If this motor is only supposed to draw 1 amp, if it's not spinning at all, it's not spinning, then it's going to draw the maximum current based on the resistance of the winding. So all of a sudden now this motor that's only supposed to be draw 1 amp is now drawing like 20 amps, right? Or more, or 30 amps. And it's only rated for 1, but it's not turning. So basically what's going to happen, it's called single phasing, because we've lost our 3-phase, now we're a single phase. And the motor's just going to heat up. So it won't spin. You lose a phase, it won't spin. It'll overheat, damage the motor, which is super important. It's why we have to have like 3-pole connections, right? Like when you throw that switch at the shop, when you use that switch, and what's the rule you're using when you're throwing that switch? What's that? What do you call that rule? When I tell you to energize a circuit, what do you call that? That is the something starts with an L. The one to keep you safe.
Could you say again, please?
Sorry, what is the rule when you grab this, when you're about to turn the disconnect on here?
Never guess it.
You got to use your
Left hand rule.
left-hand rule. Can't stand in front of it, right? You can't stand in front of it. All right. So, okay. All right. And anytime we turn one of these switches on, right? There's different symbols, different types of switches, different symbols. But like, for example, I have a 3-pole switch. 3-pole means I'm breaking 3 wires at a time. L1, L2, L3. And usually sometimes it'll be indicated there's a dashed line. What's a dashed line typically mean in these schematic symbols when you have a dashed line? Or if I have a dashed line like this, what's that mean? What's the purpose of that dashed line?
Mechanically connected.
Yeah, exactly. So anytime you see that in a schematic, that means mechanically connected. So that means like with that disconnect there, I only have one switch, but it makes and breaks all those connections at the same time every time. It has to. If you could break one at a time, then you risk single phasing the motor, damaging all your equipment, right? So that's not a good thing. So that's a 3-pole disconnect. Okay. So what do we talk about? Let's talk about overloads, talk about single phasing, the latching circuits. How do I jog a motor? What am I doing to like make a motor jog? Or what am I when I had a jog circuit, what was the key there? I started with a latch circuit, right? I started with a latch circuit. Right. So again, this is probably something you should be practice drawing if you haven't drawn this for a while, which you should have been drawing this week to week, but if you haven't, maybe practice.
Hello. Oh god, I didn't know I was that fast.
You can forget it in a week from now, or you can forget it after Tuesday for a little bit, but it's going to come back. So right now, this is momentary operation,
I'm-
correct? Momentary?
Yes.
Yes,
Yeah.
sir.
And I want maintain. So maintain, I got to add my holding contact, right? In order to make this jog, I had a couple ways of doing it, but basically every which way that I was doing it was just basically removing the wire, right? So I could have had that selector switch down here, right? And then by pushing it, it would just open the circuit. So that would be like a jog circuit. I could we had it the other way where like we had another rung, right? The other way that we had this, we had another rung here altogether. And then this was also an example of our interlocked button here. We had the jog normally closed up here and then normally open down here, right? So when you push it, this goes down and then this closes. Okay. So that's what we mean by jogging though, right? Whenever we're talking about jogging a motor, it usually just means momentary operation. All right. So what else? If I wanted to connect another stop button in this circuit, where would I connect it? Where could I connect it? So could I connect another one, say A, B, C? Where would I connect it? A, B, or C? If I want to connect another stop. Best place.
Probably
C.
A, sir.
A.
A is the best place. I got to connect it. How do I connect it? What's the word I'm looking for? Basically, when you're electrician, you're wiring things in parallel and in. What's the other way?
Series, sir.
Yeah, and as we learned, even though you may not have loved them at the time, most circuits are combination circuits, like this latching circuit, right? It is a combination circuit. But we want to connect multiple stop buttons in series, right? Then my iPhone just perked up there because it just thought I was talking to it. Series, not Siri. Okay, so series. And yeah, A is the best spot. We want to add more stop buttons. We would add those in series. Again, we have a machine or piece of equipment, needs multiple safety stops to operate. Sometimes, right, equipment has additional safety. So you have like a foot switch and you have to put your foot on the switch. Or sometimes you have to there's 2 buttons and you have to put your hand on each button. And physically they're actually far away. So you have to so that way you cannot possibly have your hand within, say, like a hammer or a shear or something like that. So there's a lot of ways that you have to press this button and this button, but you're basically stops, right? And then you can activate the machine. So actually, what you could have is you could have another stop here, and these could be this could be A and this could be B. And then the start would actually be you got your hands on here, and then you would actually have to step on another a foot switch to operate the machine. That way you're forced to keep your hands away from the machine and start it with your foot, right? That's kind of common for some heavy presses and stuff like that sometimes. So, but adding more stop buttons, we add a series. Would C work? Would C work? It would. C would technically work, but it wouldn't, it's not really good practice, right? Our stop controls, we want to put them all in series at the beginning of the circuit. And then, you know, at the end of the circuit, we would have just our overload limit and over limit, and that's it. Okay. If I have a there's a question here somewhere on an assignment too, and it's kind of good to look back on some of those assignment questions. I have a 2-amp motor. We know that there's a calculation that you can do, and you've probably done this in your commercial class too, maybe. There's a calculation that you figure out the maximum size of the fuse. But if I'm putting this motor on a breaker panel, right? 2-amp motor. What's the minimum size overcurrent protection I can use? So I got this little 2-amp motor. I gotta install it in my house. What would that be? So you know, sometimes you go like 150% or 175% depending on the motor. But I can't really do that, right? Would it be okay just to hook this up to a 15-amp breaker?
Yes.
Yeah, there was a code rule. There's a question specifically about that, right? Because I can't have anything less than the 15-amp in my house, right? So the code says that's okay for overcurrent protection, right? And that has to be true, because if you think of like your bathroom fan is like 0. It's like a third horse. It might be like half an amp or something like that, right? So that's nothing. But it's considered protected from overcurrent from the 15-amp breaker still, right? Which is fine. However, what this does not provide now is does not provide thermal protection, right? Doesn't act like an overload, right? So this type of motor, small motor like this, you're connected to 15-amp breaker. A lot of times it would have a built-in thermal protection, right? Built-in overload protection, right on the motor. Might have a little button to reset it. Might just have to cool down to reset. Okay, but yeah, this is acceptable when we're using a breaker. However, if we're using fuses, we got to size it closer to the motor, right? All right. So I think looking at everything here, and I'm just kind of looking at your test too. I feel like I've covered everything. What's an advantage? What's some advantages of using a contactor over a manual press start button?
Actually, no, I'll go back to my original answer.
There's gonna be some multiple guess, yeah. There's gonna be some true and false, and there's gonna be a couple drawings and maybe like a short answer type thing, but the short answer being like completing connections. What's an advantage of a contactor with a coil versus a manual start? That you have to press a button. What's one? Contactor, you can remote.
Yeah, you can remote with the
Exactly.
low current.
Yeah. So we can remotely control it, right? And in this case, all our buttons are on the door panel, but we could actually have the buttons to start your motor. You could wire your motor in your commercial class and then go over to your PLC room and then energize the motor from a laptop. You could have a push button upstairs. You could have a push button in the library to start a motor in our shop, right? It doesn't matter. You can have it remotely connected. And another big advantage is that if our motor here is 600 volts, our coil doesn't have to be 600 volts. Our coil could be 24 volts, right? So we can connect it to extra low voltage. And this could be 600 volts, 200 amps, size of your house panel. But we could use a little itty bitty 24 volt coil to connect it, right? So the control voltage does not have to be the same as the actual power source, right? They can be different voltages, or they can be the same. right? There's a lot of flexibility. All right. I think that's pretty thorough. If you followed along with everything here, I don't think you should have any surprises, right? I'll send out another thing, another ping or whatever. I sent an email on Slate. It's been on the calendar for weeks now on Slate. The room number, right? Make sure that you go to the right room. It's in a C building there. I believe it's C308. I'll double check, but it's what I emailed you this morning. It's on the Slate calendar, and I'll ping you again on Teams. Make sure you're there. Make sure you're not there late, right? At 20 minutes after the test starts, there's no admittance. It's an hour test, right? We had I got the room from 8. I got the room from 8 to 10, but it's an hour test. I give everybody time and a half to allow for accommodations. So if you have accommodation, you should be good. That way, it just keeps everybody in the same room. And then that way, you don't have to write it in the test center. Okay. So everybody will have up to an hour and a half. It's an hour test. So if you're done like quickly, you don't feel weird. That's okay. If it takes you longer, that's okay too. And that's it, right? But no admittance after like 8:20, right? It is 25% of your mark. So make sure you're there a bit early. And if you're not sure where the room is, maybe find it. Get there early and find it. But it's just basically you take the catwalk, right? The walkway. So they go to A building on the 3rd floor there's that walkway that takes you right into the C wing, and that's on the 3rd floor. And then it'll just be go right down the hallway and it'll be down there. Okay. Any questions? Further questions? Any confusion or anything you need to clear up? If you do, you can always email me. As long as it's not too late or too early in the morning, I'll probably get back to you in a good time. Other than that, I think that's it. I think we're good.
Thank you. Thank you.
All right. Appreciate your time. And
Thank you. You too.
see you tomorrow.
Thank you, sir.
All right. Thank you.